Hello. In last week's video, I showed you the mathematics behind the discrete Fourier transform, an operation that turns a signal that varies with time into a spectrum of the frequencies in that signal. In this week's video, I walk you through a program written in JavaScript that implements the DFT. You'll recall that in the DFT, the signal has been sampled at a certain sampling rate. This sampled signal is then subdivided into a series of time slots of fixed length, in the sense that each time slot contains a certain number of samples. For instance, if the signal was sampled at a rate of 44 kHz, or 44,000 samples a second, and each time slot contained, say, 1,000 samples, then each second of the signal will contain exactly 44 time slots. We then apply the DFT independently to each time slot, calculating frequency strengths that apply just to that small segment of the signal. The input to each DFT operation is therefore a fixed number of signal values. We assume that there are capital N samples in each time slot. In our example, capital N would be 1,000. Those individual signal samples are represented by little f, being labelled F0, F1, F2, etc., up to Fn-1. The counting, as usual, starts from 0. From those n samples, we can calculate the same number of frequency components, represented by capital F this time. You see the formula for doing this on the screen. We calculate n frequency strengths from each sample, using k as the counting variable. K counts from 0 up to n-1. The formula contains an optional term, that divide by n at the start. Some versions of the equation use it, some don't. I've seen both in about equal numbers, and I don't know what the official position is. When I was taught the Fourier transform, the equation didn't include it, so I don't either. Here I have taken one of those capital F terms and written out the formula for it as a series of terms to be summed. This is achieved using a counting variable little n, which increases from 0 to capital N-1. In each case, we raise e to some complicated power and multiply what we get by the corresponding sample value, with the result being added to the running total. You'll notice that each term contains I, the square root of -1, which makes the power of e a complex number. This leads to a problem, as we end up with a series of terms that are complex number powers of e that have to be added. The problem is that in each term, e is raised to a different complex number power, meaning that they can't be added together simply as they stand. If they were all the same power of e, then at least that exponential could be taken out as a common factor, allowing you to add the sample values. You'd still end up with complex numbers in the answer at the end, but at least you would have kicked the can a little further down the road. But they're not. The powers of e are all different, and, being complex numbers, we can't just turn them into ordinary numbers and add them. We need to apply another trick. There is a mathematical identity that states that e to the power of I times anything is the same as the cosine of that thing plus I times the sine of that thing. By substituting the powers of e in the formula using this identity, we now get the terms in a form that can be added together. We still have imaginary numbers in the formula, but all the real terms can be added together straight, and all the imaginary ones can be added together straight. Here is the formula written out using the substitution. It might look more complicated, but in fact it's easier. Now there are no longer any powers of e. We can put in numbers for all the real terms and add them, and put in values for all the imaginary terms, though not for I itself, of course, and add them. The answer will come out as a real part plus I times an imaginary part. Each frequency strength, capital F, 0, 1, 2, or whatever, is therefore boiled down to two numbers. These can be thought of as a vector on an Argand diagram as shown, with a magnitude and a direction. The magnitude is the length of that line, found by applying Pythagoras' theorem to the real and imaginary parts. The direction is given in terms of the angle that the vector makes with the real number axis, termed the phase angle. For most purposes, we would probably only be interested in the magnitude of the frequency component, the strength of the frequency component, if you like. In calculating the magnitudes, all complex numbers disappear, and we are left with a list of capital N frequency component values. We start with capital N numbers, and we calculate capital N different numbers from them. So much for recapping last week. Now onto the program itself, and for once, it's a fairly short one. Here you see the screen. There are two text areas. The top one lets you enter the sample values for the time signal itself. The one at the bottom of the screen is where the corresponding frequency strength values will appear. Between them, we have various program controls. Firstly, there is a button to load the signal data into the program. After that, you must specify the number of samples that make up every time slot. The number of time slots into which the signal will be divided is determined from the number of samples loaded and the length of each slot. If the slot length doesn't divide completely into the number of samples loaded, any incomplete slot at the end will simply be ignored. The checkbox allows you to specify whether you just want to calculate the magnitudes of the frequency components or want the phase angles included as well. The button below that, marked DFT, performs the actual magic. Click it when you want the calculations performed. The text field below the button, marked slot, simply indicates to the user which slot is being processed. While short signals process almost immediately, longer ones might result in the screen not changing for some time, and I don't want anyone thinking that the program has crashed. Finally, there is the text area, where the calculated values appear. Beside each screen element, I show you the HTML code I used to create it, complete with an ID that lets the JavaScript refer to it. As always, I start with the global variables. As far as possible, I've tried to stick to the same terminology as in the equations. So the number of samples in each application of the DFT is given by capital N, and those samples will be stored in array lowercase f. The entire signal will be stored in variable signal, and this will be turned into an array at the appropriate moment. The number of samples in the entire signal is numSignal. Mag only is true if we want the magnitudes, not the phase angles, and slot offset are used to step through the signal, tackling it one time slot at a time. The list of calculated values is stored in the string result before this is copied out into the text area right at the end. Here is the function loadSignal, which is called when you click on the Load Signal Data button. It copies the contents of the top text area into string S and splits it using commas as the delimiter, storing the samples in signal. This is the point where signal becomes an array automatically. When you click on the button marked DFT, it doesn't call the DFT function directly. Instead, it calls setupDFT, which does a bit of housekeeping before getting stuck into the calculation proper. Mag only is set based on the checked or otherwise status of the checkbox inc phase. If mag only is true, only the magnitudes are required. N is set to the contents of the slot length field to determine how many samples there will be in each DFT calculation. I have arbitrarily set a lower limit of 5 samples per slot, so if you enter a lower value, the program will complain. Assuming the slot length is large enough, the program finally calls function DFT to tackle the first time slot. It sets variable slot to 1 to indicate to the user that this is slot number 1 of however many it is, and slot offset is set to 0 so that the program will read the first n samples from the signal. There is only one other function in the whole program, and it's a long one. Function DFT performs the actual calculations and writes the calculated values to the string result. The first thing it does is write the current slot number onto the screen to keep the user happy. Then it copies the next n values in the string into array f, starting at position slot offset and working its way up. The results of this particular DFT calculation will be stored in string s, before that is added to string result. Variables fReal and fImag will hold the real and imaginary components of each Fourier value as they are calculated. You might expect that, since we need to calculate n Fourier values, both real and imaginary parts, that we would need an array for both of these, but as we calculate the individual f values, we store them in string s and move on. Simple variables will therefore do. This screen and the next one all take place within a for loop that goes through all the k values for the Fourier components. These are the capital N strength values that need to be calculated and written out. Firstly, f real and f imag are set to 0. These will form running totals, and the real and imaginary components of each term in the summation will be added to them. Those components are calculated in a nested for loop, this time using small n as the count. The power of e calculated corresponds to the equation that you saw, except that it doesn't use I as the square root of -1. Instead, we use the identity that you saw, the one with cosine and sine in it, to update the real and imaginary totals respectively. You might remember from last week's lecture that some versions of the DFT formula divide the total calculated by capital N, others don't. In this program I don't, but I've included an extra line of code if you want to do that, commented out. Now before I show you the lower half of that for loop, I need to explain how we calculate the phase angle. Simple calculation, as you saw in that previous slide, is to find the slope of the vector on the Argand diagram by dividing the imaginary component by the real component and performing an inverse tangent. Easy. Well, no. There are two flies in this particular ointment. Firstly, what happens if the real part of the value happens to be 0? JavaScript does not like us dividing by 0. Well, that's not really a problem. We just test the real part to see if that's the case. If it is 0, then the phase angle will be 90 degrees if the imaginary part is greater than 0, and minus 90 degrees if it's less than 0. The other problem comes from the vectors, which are on the negative side of the real axis, on the left-hand side of the diagram. If you look at the graph of the tangent function, then you find that once you go beyond the problematic value of 90 degrees, the graph simply repeats itself. Therefore, working backwards from a tangent value means the phase angle could be between minus 90 and plus 90, or bigger than 90. For this reason, when we calculate the phase angle, we look at the real component of the vector. If it's negative, the phase angle must be made 180 degrees bigger than the value we first get. Here's the second half of that for loop that you saw before, and you can see that calculating the phase is quite involved. If the real component is 0, the phase is either plus pi over 2 or minus pi over 2, with the sign matching the imaginary component. Otherwise, it's calculated from the inverse tangent and adjusted by adding pi radians if the real component is negative. Yeah, I suppose I could have calculated the phase angle in degrees. I prefer degrees to radians, but it would have meant more code, and to be honest, I really couldn't be bothered. The easiest thing to calculate is the magnitude, which you can see in the middle of that screen. This is written straight out to string s. If the phases aren't required, then that is followed by a comma to separate it from the next magnitude value. Otherwise, it is followed by the phase angle and a carriage return. Then the loop iterates for the next value of k. Here's the end of the function DTF. The string s is added to the string result, which holds the entire series of calculations. Then the program tests to see if there's at least one more slot to go. If so, slot offset is advanced by n, so that the next set of values are loaded in, and the function is called again. You'll notice that I've chosen to call function DFT not in a for loop, but as a repeated call to the function using setTimeout. This is to prevent the program taking up too much time and JavaScript assuming that your computer has crashed. While small sets of data produce results almost instantaneously, with signals of any substantial length, you might be twiddling your thumbs for some time. If DFT detects that it has reached the end of the signal samples, or at least so close to the end that it can't extract another complete time slot, then it writes string result to the text area, and the program terminates with a done message. OK, let's take the program for a spin, shall we? See what sort of results it produces. I used OpenOffice Spreadsheet to create a file of 200 samples, separated by commas, representing a pure sine wave. The wavelength, for want of a better word, of the wave is 80 samples, i.e. it repeats every 80 samples. So the entire signal is 2.5 waves. I ran the signal through the DFT program and got 200 comma-separated values out, which I pasted into a text file. I chose a time slot size of 200 samples, i.e. the program treated the entire signal as one large sample. Choosing smaller time slot sizes gives the same basic results, but it's harder to read the smaller graphs that result. It's a fairly easy matter to load these into a spreadsheet, such as OpenOffice, as long as you specify in the open function that it's comma-separated values, or CSV, that you want. The screen shows you how to do it in OpenOffice. I dare say that it's the same with other spreadsheets. And here's the result of running the program on the sine wave. That peak on the far left of the graph is our sine wave. It won't have escaped your attention that our peak has a mirror image on the right-hand side of the spectrum. This is a feature of the discrete Fourier transform and not simply a bug in the program. Shame on you for thinking that. If you go on the internet, you'll find several people complaining that their DFTs do exactly the same thing and produce a mirror image spectrum. It's in the nature of the Fourier transform equation to produce a mirror image on the negative half of the frequency spectrum. Of course, we don't consider negative frequencies, but the maths doesn't know that. As far as it's concerned, those negative frequencies are there. You'll see from the equation that I've added that every cosine can be made by adding together two exponential terms, twin brothers, except that one is positive and the other negative. The fact that the signal is limited to a fixed number of samples, the evil twin, as it were, appears at the top of the spectrum. This is an aliasing effect. You'll find that exactly the same thing happens when we implement the fast Fourier transform in code. If it bothers you, you can always simply chop off the right-hand side of the graph and pretend it doesn't exist. Now I've created another signal of 200 samples, again containing a pure sine wave. However, this time the wavelength is 55 samples, i.e. it has a higher frequency than the previous one. We should expect a single peak, but this time slightly to the right of the previous position. And that's what we do see. Again, the peak has a mirror image on the other side of the graph, but we're concentrating on the peak on the far left. That's our sine wave with wavelength 55. So, what happens when we add those two sine waves together and process the results? Here is the graph of the 200 samples, which are the simple sum of the previous two signals. We should get two peaks, one for the 80 sample wavelength and one for the 55 sample wavelength. Drum roll, please. Behold, two peaks. The peak on the left is the one for the 80 sample wavelength and the other is for the 55 sample wavelength. And you can wipe that surprised look off your face. Didn't you expect it to work? Hey, it's me. So, there you are. The program has quite a few twists and turns, but is actually one of the shorter projects I have described on this site. I hope you find this code useful. Please do let me know how you've adapted and improved it for your own signal processing programs. Next week, I shall be describing the fast Fourier transform, which is the standard way of turning a time signal into a frequency spectrum. Thank you.